Good evening, everyone. So, we were talking about silica fume in the last class, and I was talking about the fact that when you collect silica fume, it's collected with a very small particle size and the density is extremely low, because of which bulk handling of silica fume becomes quite difficult. For that purpose, what we typically do is condense the silica fume by compacting it into particles that are of the same size as cement. Okay. So, what we get is a condensed or dry densified silica fume, but as we discussed also that sometimes silica fume can also be made available as a slurry, in which case it is easy to disperse in the concrete mixture. If it is in the dry densified form, what you need to do is have a good mixing strategy and use a very good super plasticizer to completely mix the material into the concrete. Otherwise, what you will have is these agglomerates of silica fume will sit in the system without really reacting, and you may actually end up having a scenario quite similar to alkali-silica reaction, in which small condensed particles of agglomerates of silica fume can start acting like reactive siliceous aggregate rather than the reactive mineral admixture that silica fume is known to be. In fact, there is research worldwide which shows that these silica fume condensed particles, if they are not able to disperse properly and react pozzollanically, then in the long term you may get some risks of alkali-silica reaction. Alright, so in terms of physical properties, the particle size typically is less than 1 micron. So, cement has an average particle size of around 15 microns. So, here we are talking about a completely different order of magnitude in terms of the particle sizes. The average size is close to about 0.3 to 0.5 microns. So, we are talking about very small particle sizes. The bulk density, the as produced state is 130 to 430 kilograms per cubic meter, but when you dry densify it, you can almost triple that to about 5 to 700 kilograms per cubic meter. So, because of that, since it is bulky, even after dry densified, we do not typically get it in bags of 50 kilograms, we get it in bags of 25 kilograms. Okay, generally what happens is when you have lower specific gravity material, obviously the bulking of the bag will be there. If you try to put in 50 kilograms, the bag will still be quite massive. So, because of that, with 25 kilogram bags. Okay. Now, specific gravity of the particles is quite similar to what you have for fly ash, about 2.2, not that much different, because again this is silica particles. So, these are having a specific gravity of about 2.2. And the surface area, which cannot be measured with the help of Blaine's air permeability test, because the air simply cannot permeate through a bed of the silica fume particles since they are so fine. So, you do not really have the spaces in between for the air to flow through. Because of that, we have to adopt other techniques to determine surface area, and this is called the BET technique, and this BET is based on the principle of adsorption. Of course, we are not here to learn the technique, but I just wanted to give you a glimpse as to what happens in this case. You have nitrogen gas which is made to condense on the surfaces of these particles. Okay. So, when can nitrogen condense? When it is extremely at a low temperature. When typically temperatures of about 77 Kelvin are used in this instrument, where nitrogen basically forms a layer on the particle. So, the more the surface area, the greater the adsorption of the nitrogen. Okay. Similarly, you can also do adsorption studies using water vapor, but most commonly preferred methodology is to use liquid nitrogen to condense on the surface of these fine powders. So, based on that, you can work out a surface area between 13 and 30,000 square meters per kilogram. So, it is sort of a completely different range as compared to your cement particles. Alright. So, cost, of course, you know very well that this is a material that is coming out of a very highly specialized industry, because of which the cost is very high. About 5 to 6 times the cost of Portland cement is what you will end up paying for silica fume, and that is because silica fume is a material that is obtained from a specialized industry, and again the conditions of usage of silica fume are also quite different as opposed to fly ash or slag, which are from more regular sort of manufacturing industries. Okay. So, silica fume is expensive, so you really need to justify why you use silica fume in concrete. Okay, so, only if the situation demands and you need the kind of performance that you get from silica fume, only in those cases you will actually end up using silica fume. So, because of that, we also need to maintain a low replacement level. Typically 5 to 10% is what is usually done, but there have been instances when 15% replacement also has been used. But cost is not the only thing because of which the replacement is low. The other aspect is you are using extremely fine particles, so there is going to be a massive increase in the water demand. Even if you compensate with super plasticizer, your mix is going to get exceedingly sticky because you have such fineness in the mix. So, because of that, you need to ensure that you keep the replacement level to a minimum generally 5 to 7% is more commonly adopted as cement replacement. Okay. Now, of course, there is not much to discuss in terms of the performance. The benefits are obviously from the extremely fast pozzolanic reaction because of the fine particle size as well as the high purity of the silica in the silica fume. As we discussed earlier, nearly 90% silica is present, because of which there is a very large degree of reaction, pozzolanic reaction, and it happens quite quickly also, because of which silica fume replaced mixes can get the same strength performance as ordinary potent cement mixes within the first 3 days itself, okay, sometimes as early as 1 day. Now, the main problem when silica fume is used is its effects on the fresh properties of the concrete. Now, hardened properties generally with silica fume, most of the properties are positive. I will talk about that in just a minute. But in terms of fresh concrete, because of this extreme fine nature of the particles, there is an additional degree of cohesion in the concrete. Okay, while that may be a positive attribute in certain cases, for example, when you are doing flowing concrete, in that case your self-compacting concrete is able to maintain the cohesion and prevent segregation, right. Or if you are making a grout for a post-tension application, right, where your grout has to actually flow through very small constricted spaces without getting segregated, the silica fume particles do very well in actually reducing the segregation. Okay. But the problem with that is felt in the regular concrete construction. When you do a regular concrete construction, if your mix becomes highly cohesive and sticky, compaction and finishing become a difficult task, especially finishing. Okay. So, that is one major issue, and the other aspect is that your slump loss is also large, because a lot of the water gets lost in adsorbing on the surface of these extremely fine particles. Okay. Now, of course, because of silica fume being so fine, there is no question of any bleeding from silica fume mixes. Now, bleeding is obviously a negative thing to happen in concrete, but there is one positive attribute to a little bit of bleeding from the concrete, is that it provides a sheen on the surface of your concrete that protects the internal water from evaporating. Now, I am not saying concrete should bleed because of that, but I am just saying that in situ concrete, when we typically cast it, especially in horizontal elements like slabs or beams, there is a rise of water to the top. Okay. The detrimental part of that is obviously that this water is going to increase the local water to cement ratio at the cover concrete zone, but the advantageous part is that when this water comes up to the surface, it prevents the atmospheric drying of the internal water from the concrete. Now, with silica fume, since there is going to be no bleeding, your concrete is going to be susceptible to drying from early stage itself. Now, what do you think is the problem with that? Plastic shrinkage, essentially shrinkage of the concrete while it is still fresh, and that will lead to cracking, right, because only the surface of the concrete wants to shrink, the rest of the concrete is dimensionally stable, because of which there is a restraint which causes the cracks to appear on the surface. Again, not a structural issue, we will discuss more about this later, but you do not want obviously surface cracks to appear, because aesthetically it is a problem. Secondly, durability may be an issue, because if there is cracking, obviously water can get into the cracks. So, mostly with silica fume, your consistency is going up extremely high. Consistency, you know very well, is the minimum water required to wet the paste, right. So, with 0% silica fume, when just plain Portland cement is there, the consistency is more of the order of about 30 to 32%. With 30% silica fume, that is inordinately a high amount of silica fume as a replacement, it goes up all the way to about 40 to 45%. We are mostly concerned with this range here, because that is mostly what the replacement level of cement would be, about 5 to 10%, but even there you see a substantial increase in the cohesiveness of your mix, which causes the consistency or water requirement to go up. Okay. Now, again, some research results are presented on this side with respect to the effects on the heat evolution patterns. So, remember we discussed that the dormant period relates again to the early period of cement hydration, beyond which you start the main silicate peak, and you can see here with very high amounts of silica fume, you can actually get a situation where your peaks beyond the silicate peaks are getting excessively enhanced. Okay. So, now in this case, main hydration peaks are also getting severely accelerated. Okay. Now, what is happening here? Silica fume requires the presence of lime for production of CSH, because it is a pozzolanic binder, right. What is happening here is your silica fume particles, being extremely fine, have a very large surface area around them. Okay. Now, because of the high surface area, they give a space for your regular cementitious hydrates like CSH to nucleate, to grow. And because of that, whenever any fine material, fine additive is added to a blend with Portland cement, you will start seeing an increase in the rate of hydration. Okay. When very fine materials are used as replacement for Portland cement, you will start seeing an increase in the rate of heat evolution in the early stages, because more and more CSH is now capable of forming on the new sites which are provided by these fine particulate matter. It is not that the silica fume is reacting. The silica fume may not be reacting in that stage, but the surface of the silica fume particle, which are very high surface area, are providing sites for nucleation. Okay. So, there are chances of early age concrete being quite different with silica fume as opposed to with Portland cement alone. Now, again this is a picture showing the fineness of silica fume particles. You can see cement particles are of this size, right, and there are some smaller cement particles also, but compared to that, on the right hand side you see silica fume particles which are much smaller. A typical particle size distribution curve is given here, and if I pick up the D50 from this curve, it will be around 0.3 to 0.4 microns. So, this is an extremely fine particle size, completely different order of magnitude as opposed to cement. Okay. Because of this, you get all these interesting problems with silica fume, primarily plastic shrinkage. So, again this is, for example, let us consider this blend here, which is a blend of cement plus silica fume, and this blend which is just cement. Okay. So, when water starts drying out between the cement particles in the case of a plain cement mix, okay, the capillary pressure that is caused by the drying out of this water can be worked out to some extent by this capillary equation, right. Your pressure is related to the surface tension, related to the surface area of the particles, as well as the water to cement ratio. So, if you consider a particular water cement ratio and use this equation, assuming the surface tension of water to be a constant amount 0.0073 Newton per meter, just substituting different surface area of a cement and silica fume particles gives you results like this. For cement, it is 0.07 megapascals. That means if you make a concrete with plain cement, your plastic shrinkage related capillary pressure which is caused when you dry the water from between the particles is less than 0.1 megapascal. So, very small pressure. So, it is not resulting in any cracking. With silica fume, the same capillary pressure rises to about 4 megapascals. Now, obviously in the fresh state, or when concrete is in a semi-solid state, it is simply not going to have enough resistance to resist this kind of a stress, 4.2 megapascals. Now, of course, there is an exaggeration based on these values that have been obtained, right. 20,000 square meters per kilogram has been used as a surface area of silica fume particles, whereas 350 for cement particles. You are using a blend here, cement and silica fume, it is not plain silica fume. But just for the purpose of argument, this capillary pressure can be actually looked at as a means of understanding why concrete with silica fume is susceptible to cracking because of plastic shrinkage issues. Okay. Now, with hardened concrete properties, there is really not much to talk about. In most cases, because of the extremely fine particle sizes, it works as a filler. Secondly, because of the pozzolanic reaction, there is additional CSH formation, because of which most of the characteristics are enhanced. Primarily because silica fume is such a fine material, it is able to fill the extremely small voids between the cementitious hydrates, and that enhances the strength of concrete, and also it enhances the modulus of elasticity of the concrete. The resistance to deformation with silica fume concrete is much higher than that with just Portland cement concrete. So, about 15% more than Portland cement concrete. In the case of durability, most results are positive. For example, here this is an example of a research study which explains the influence of silica fume on the rapid chloride permeability charge passed. Of course, we will talk a little bit about this test later on, but essentially the higher the charge that is passed through the concrete, the more permeable that concrete is. So, if you pass a low charge, that is what happens with silica fume concrete, you get a very low charge passing through the concrete, implying the concrete is highly durable. Now, of course, there is a story behind this. After this test was developed in the US, this test was developed first in the Portland Cement Association laboratories, which are now called, I think later they were called CTL, Concrete Technology Laboratories. A lot of seminal work actually came from there, PCA, Portland Cement Association. So, after this test came out, the manufacturers of silica fume found that this test was really very helpful to promote their product. And that is essentially because when you have or very fine grained silica particles in your mix, you trap all the ionic species in the glassy particles itself. Okay. When you trap all the ions are not freely moving around in the concrete. Now this test method, that is rapid chloride permeability test, or RCPT, we will talk about this again in durability section. RCPT, rapid chloride permeability test, basically what you do is you apply a 60 volt potential difference between two phases of a concrete specimen that is 50 millimeters thick. You expose one phase to sodium chloride, the other phase to sodium hydroxide. The science is that because you are driving this potential, the chlorides are driven through the concrete towards the anode. Okay. The chloride being negatively charged go towards the positively charged electrode. Okay. Now the problem here is when you have concrete which is saturated, you know that there are ions in the pore solution of the concrete. We talked about the fact that there is sodium, potassium and hydroxyl ions. When you apply a potential, obviously those ionic species also start moving around, right. The charge carrying ability of the concrete will depend on the amount of ions present in your pore solution. So when you introduce a finely graded silica in the system, amorphous silica in the system, these ionic species, sodium, potassium and hydroxyl ions, get trapped inside the glass, that silica glass basically. They get trapped inside the silica glass, because of which charge simply cannot flow through these systems. So when you test a concrete with silica fume, it is no surprise that you are actually getting a result that is extremely good. Now of course we are using the same result to also propagate the concept of limestone calcined clay cement. Same thing is happening there also. Okay. Even in that case, your alkalis or the conductive part of your cement is simply getting captured by your mineral additive, right. That is the glassy nature of the mineral additive, simply trapping these alkalis and preventing them to move around. Okay. So when you do not let your charges move around in the concrete, you are not able to pass that much current through the concrete, and as a result the charge passed in this test becomes quite low. Okay. But nevertheless, even with other test methods like water sorptivity tests and things like that, you can still prove that when you use fine particulate mineral additives like silica fume as replacement of cement, your performance definitely improves. But RCPT somehow has become a test that silica fume manufacturers have used tremendously to their advantage. If you look at their brochures and publications, you will often see the mention of this test, because this brings out their material in a far superior way as compared to any other test that can be used for durability applications. Anyway, but nevertheless, it still goes to show that silica fume concrete is more durable as compared to plain cement concrete. Now, apart from strength enhancement and durability enhancement, your hardened concrete properties, most of them are very good. Expansions due to alkali-silica reaction are definitely improved or reduced when silica fume concrete is used, and the same is true for any mineral additive, even fly ash or slag. When you use it as a cement replacement, you are going to be reducing the alkali-silica reactivity. Again, why do you do that? Because I just told you, because of which the RCPT performance is good. What happens there? Alkalis are getting trapped in the glass. Alkalis are simply getting trapped in the pozzolanic glass or silica glass that is present in these materials. So if you do not have alkali, of course the alkali cannot react with the reactive silica of the aggregate. Okay. Now having said that, let us come back to the pozzolanic reaction. You are again reacting the amorphous silica, reactive silica, with calcium hydroxide. Now why does not this amorphous silica want to react with the alkali? Yeah, we discussed already. That was a question. Anyway, so anyway, there is a size effect. So again, the aspect is that when your finely graded silica particles are used, they trap the alkalis into a non-expansive gel, because of which this alkali is not able to react with the reactive aggregate, right. And this happens very early in the process of mixing the after mixing the concrete. So this really does not create a problem like reactive aggregates do, which happens in the very long term. All right. Now there are effects on microstructure of the concrete that have been published all over the world. When silica fume is used, you definitely get a much denser structure. You can see here, this is 100% Portland cement. Okay, this is a backscattered electron image of concrete which is showing 100% Portland cement. This is 10% silica fume, 25% silica fume and 45% silica fume. So you see very clearly, as you replace more and more cement with silica fume, you are increasing the level of packing of your cement paste, and you essentially end up with a system which does not show much porosity. Okay. Now, interestingly, there is also other research which shows that the effects of silica fume can be better demonstrated in mortar and concrete as opposed to paste. What do I mean by that? If you are testing paste, cement paste, if you are replacing cement with silica fume, all that is happening is the porosity inside is getting filled up to some extent, okay. But the cohesive strength of the paste is not that much affected, maybe marginally 5 to 10% affected by the substitution of cement with silica fume. The same test, when you do it on mortar, produces a completely different scenario. Why do you think that happens? What could be different in mortar which is not happening in paste? In mortar, people have reported strength enhancements up to the order of 30 to 40%, and durability in concrete, people have seen, of course I have showed you the result with rapid chloride permeability. With other tests also you see a much better performance when silica fume concrete is used. So, what is happening in mortar and concrete which is not there in paste? ITZ, you do not have any interfacial transition zone in paste. So, in mortar and concrete, the ITZ, you know very well, is responsible for most of the negative effects of cement concrete. So, if you are strengthening the ITZ, or if you are increasing the particle packing around the ITZ, you are obviously going to get much more benefits when silica fume is used. So, that is what you see when you look at research papers. If you look at the research papers that look at the effect on paste with silica fume, you will see that there is not that much of an enhancement in properties, whereas in mortar and concrete you can definitely see the distinct benefits of using silica fume. Of course, this is just showing you the expansion due to alkali-silica reaction and the reduction when more and more silica fume is used as a replacement for cement. Now, again this is showing a real chloride test called chloride diffusion test. Okay, this is basically the chloride diffusion test. Now, what is chloride diffusion? Basically, it is a movement of chloride from a zone of high concentration to low concentration. So, this means that if you subject your concrete to a chloride environment, the chlorides from the external environment penetrate the concrete because of the concentration difference. This assumes that your concrete is saturated. Okay. Now, this test is done with a concrete specimen that is placed inside a chloride solution, and after some time you remove this specimen and you start removing material from the surface according to the depth, okay. And each of this sample that you collect from the specimen, you grind it to a powder and measure the amount of chloride. So, what that tells you is how much chloride is at the top, how much chloride is the next 1 millimeter, 5 millimeters, 10 millimeters and so on. And then what you need to do is plot the chloride concentration against the depth, and from the curve that you get, you need to calculate what is something called diffusion coefficient, which is a material characteristic at that particular age. So, if you are measuring this at 28 days, we call it the diffusion coefficient at 28 days. Why should we be specific with respect to time? Because with increased number of days, the microstructure of the concrete changes, because of which you may get a completely different result. So, here what is being shown is when silica fume replacement level is increased, you have a massive drop in diffusion coefficient. That means your capability for chloride to diffuse through the concrete keeps reducing as you increase the level of silica fume in the concrete. So, this is actually a true positive result. In the case of RCPT, you may get a false positive also, but for the most part it also reflects the fact that your concrete is more durable with silica fume. Generally, corrosion rate is reduced significantly when silica fume is used, because obviously there is low permeability of silica fume concrete, because of which oxygen and moisture cannot be easily available to propagate the corrosion. Then you also do not have sufficient points for the chloride to enter to really cause the steel corrosion to happen, right. And then your resistivity of the concrete, that means inverse of conductivity. Your resistivity of concrete becomes so high with silica fume that the ions which are needed to mobilize for corrosion to happen simply do not get the opportunity to do that. Okay. So, high resistivity and high impermeability are the reasons why concrete with silica fume performs very well with respect to corrosion resistance. Carbonation depth, this may be a matter of dispute, but in general it is lowered again because your permeability is of a much different magnitude, much lower as compared to ordinary potency. Abrasion and erosion resistance are very good, and that is one reason why silica fume concrete can be quite suitable for applications in hydraulic facilities, wherever you expect a lot of aggregate or large boulders of stone to drop from massive heights. That causes a lot of erosion and abrasion on the surface of the concrete, and for that purpose utilizing silica fume could be a very beneficial thing. Fire performance of silica fume concrete is not very good. And why do you think that may be the case? Yeah, when fire happens, heat is generated in the concrete. When heat is generated, there is moisture in the concrete that has to come out, and this moisture wants to come out almost immediately by transforming to steam, right. In normal concrete, there is enough connectivity, the ITZ, for the steam to come out without any difficulty. With silica fume concrete, the steam can actually build up within the system and cause explosive failures happening to the concrete. So, this actually was happening, this was found when the tunnel linings in the Channel Tunnel between England and France. Okay, you know that there is a Channel Tunnel which links England and France by road, and that goes right under the English Channel, right. And this Channel Tunnel, there was a petrol tanker that actually caught fire inside. So, there was very high level of heat inside, and the tunnel linings which were made with high performance silica fume concrete collapsed almost instantly. That is because the water inside started converting to steam, and it causes the concrete to burst out. So, all the linings were simply destroyed. Okay, what people started doing is looking at how we can learn from this and make silica fume concrete also fire resistant, in which case what they did was they started putting plastic fibers in the silica fume concrete, and what happens is at the high temperature the plastic fibers would melt, leaving behind the voids, and then the water will be able to come out as steam through those voids. But again, we do not really worry too much about fire performance, except this is an extreme event obviously which generates this level of fire. We do not really give the kind of emphasis that is happening in this particular case for fire performance. Let us look now at granulated blast furnace slag. We discussed earlier that it is typically not included as one of the mineral admixtures or pozzolanic additives. It is called a hydraulic cement on its own, okay, because slag can react on its own, but then the reaction is extremely slow and needs some activation. This activation typically happens in the presence of Portland cement. Now, of course, formation of slag happens in the blast furnace. You know this process quite well. You have the iron ore which is fed into the blast furnace along with limestone and coke. The limestone essentially is a flux that reduces the temperature at which the ore will melt, and ultimately all the impurities in the ore are collected along with the limestone and brought out as slag. Okay. And this slag is in molten form, it has to be immediately removed and quenched to form the blast furnace slag clinker. So, quenching of the slag happens. Quenching means sudden cooling of the molten material, and that leads to the formation of blast furnace slag clinker, and then, or if you let it cool very slowly, you get the air cooled slag, which ultimately forms a very hard and good aggregate. Okay. People can use air cooled slag also as aggregate. Okay. But what we are interested in from the perspective of supplementary materials is the use of slag in the granulated form. This is the quenched slag, which is then ground into a fine powder and used as ground granulated blast furnace slag. So, you will often see slag represented as GGBS or GGBFS, ground granulated blast furnace slag. Now, of course, there are other types of slags also which you find from the industry. Increasingly you see a lot of research papers also coming out from other type of slags like steel slags, ferromanganese slags, copper slag and so on. In fact, copper slag is also allowed as a partial replacement for fine aggregate in concrete. If you check IS 383, which is basically the Indian specification for aggregates in concrete, it tells you the different sources of aggregate that are actually permitted to be used in concrete, and you can also see the amounts to which they are allowing you to do the substitution. Okay. Unfortunately, many of these slags that are obtained in different processes are not very suitable for cement making because their chemistry could be unstable. For example, they may be able to help in the initial stages, but in the long term their chemicals or the ingredients that may be found in these slags may not be suitable for reaction or may not be suitable for proper performance of the concrete. Okay. So, you need to be very careful with the kind of material that we use as cement replacement. The steel slag, which is also available from a different kind of furnace, is called Corec slag. Now, Corec slag is very interesting because it is a very reactive form of ground granulated blast furnace slag, and this high reactivity slag is obtained in certain types of manufacturing units, and it is also quite suitable for being used as a cementitious replacement. But once again, you need to be quite sure what is the process from which you are getting your slag, so that you know exactly what reactivity you may be likely getting from this kind of slag that you are using. There is another process possible to produce slag, it is called pelletization. So, what happens here is this liquid slag which is coming out from the blast furnace is fed onto a vibrating feeding plate, and then it is thrown by a rotating drum and this process of getting thrown from rotating drum is able to form small pellets, and depending upon the size of the pellets you can collect the granulated material at one side and the large pellets on the other side, okay, because granulated material will be the small pellets which get cooled very rapidly because of this fall, okay, and then once they are cooled they form the granulated slag. You can take this pelletized slag and also grind it to get reactive blast furnace slag, but then again you must be careful about not calling it GGBFS, it should be still called pelletized slag, because your reactivity may be quite different as opposed to what you get from the quenching process. Okay, this is a Correct slag from South Africa. Again you can see the highly angular nature of the slag particles. Slag again is ground from the quenched material, so obviously it is going to be quite angular. In this case Correct slag is showing high reactivity primarily because it has got a very highly irregular structure. Specific gravity of slag is close to cement, about 2.9. So when you replace cement with slag you do not see that much of a change in the volume of the powder that you have, whereas all of the mineral additives which are silica based like fly ash or silica fume may end up increasing the volume of the paste significantly in the early stages. Bulk density is again about similar to that of cement, slightly less than cement but similar. Fineness again depends on how much you grind the slag, typically it is ground to a fineness which is similar to that of cement, about 300 to 350 square meters per kilogram, and it typically replaces about 40 to 60% of the cement in concrete. Okay, you are allowed up to 70% replacement. If you look at the standards for Portland slag cement, it tells you that slag up to a limit of 70% can be used as cement replacement. The reason for that is obvious. Why do you want to use a high amount of slag? Because it is hydraulic, it is a hydraulic cement, it is not a pozzolanic additive, it is a hydraulic cement, because of which it can substitute a larger fraction of your cement. So most of your Portland slag cements that you get in the market would have about 50% slag in them, and generally if you go to any concreting application also they would be using slag usually at a 50% replacement level. So what do we expect from slag? Generally there will be a marginally delayed reaction. I discussed this earlier that the effective time that the slag mix may need to reach the level of the potential development of Portland cement may be about 3 to 7 days, but it may also not be true. You may actually get slags that are much more reactive and sometimes equally reactive as cement and lead to very good performance at very early ages itself. Assuming again that you do adequate curing, in the long term you can expect better microstructure and durability as compared to ordinary Portland cement concrete. Now of course primarily when we are talking about slag, we are talking about its potential for chloride binding. Okay. Now if you remember, the aluminates that are present in your cement react with sulfates, right, in the early stages of cement hydration to form ettringite, which later gets converted to the AFM phases. Okay. Now if you have a large amount of aluminate in the system, it also shows an affinity for chloride ions. Aluminates can also show high affinity for chloride ions. So generally if you look at the design for concrete in a marine environment where a lot of chlorides are present, the choice of a high C3A cement is usually good, because the C3A can actually bind the chloride ions. But another way of doing this is to use mineral additives which have a high alumina content, especially alumina that is reactive, and in slag you get that reactive alumina which is able to bind the chlorides. Okay, so because of high binding of the chloride you end up reducing the extent of chloride that can get to the level of the reinforcing steel, and that obviously enhances the performance in a chloride environment. So for marine applications generally slag is known to be the best substitute for cement. Up to 50% slag is almost routinely used as cement replacement for all marine applications. Now obviously slag is a latent hydraulic system. If you let slag react on its own with water, it may take a substantial period of time before that reaction gets anywhere. So if you do some activation of the slag, it leads to a faster reaction, and activation typically is happening primarily because of the alkalis that are present in the system. For example, the alkalis that are contributed by the cement and also the sulfates that are contributed from the cement. That is basically gypsum that is present in your system also acts as an activator for the slag. Now the amount of reactive silica in the slag is obviously important from the perspective of how fast it will actually end up reacting and produce the CSH. The fineness of the slag, I mean that is that is quite obvious, and just like in the case of Portland cement system, higher the fineness, the faster will be the reactivity of the system. Okay. And in the early stages of hydration, if the temperature is high, that causes a further acceleration of the hydration process of slag. So, hydration of slag basically happens because of alkali activation or sulfate activation or mixed activation. You can actually have a mixed activation in which both alkalis and sulfates are present, just like in the case of ordinary Portland cement replaced partially by slag, and that is where you get a mixed activation. So, what happens when alkalis are used to activate? So, alkalis like sodium hydroxide, sodium carbonate, sodium silicate, these could be used, sometimes even combination of the materials can be used to actually hydrate the slag, and this hydration of the slag leads to the formation of CSH, CaH, that is calcium aluminate hydrate, and the galenite phase, which is a calcium aluminate silicate hydrate. Okay. Now, what is interesting is people often call this system as alkali activated slag system, alkali activated slag. You may refer to this in literature as AAS, alkali activated slag. Okay. This is also from the same family of materials that is sometimes called geopolymer. Most of you would have heard the term geopolymer, but alkali activated slag is truly not a geopolymer. What is happening in an alkali activated slag system is that the alkalis are activating the hydration of the slag, whereas in a geopolymer what the alkalis are doing are the polymerization of the aluminosilicate. For example, if you choose calcined clay, clay is an aluminosilicate, or if you choose fly ash, which also has alumina and silica, if you choose these materials, you will get a binding between the aluminosilicate chains or aluminosilicate molecules and lead to the formation of a 3-dimensional polymer network. So, that is called a geopolymer. Slag based systems are not geopolymers, they are simply alkali activated slag systems. Sulfate activation leads to the production of slightly different kind of products. You can activate it using gypsum, hemihydrate, anhydrite, or other alternative forms of gypsum like phosphogypsum, and the products that are forming obviously will include CSH, that has to form in all cases involving slag, but in this case you may form ettringite and aluminum hydroxide. Okay, so, you form a completely different hydration assemblage as opposed to the case of alkali hydration. So, what will happen in the mixed activation when both alkali and sulfate sources are present? Obviously, it will form all of these compounds. You may end up forming all of these compounds depending upon the reactivity of the slag. Okay. So, all the compounds CSH, calcium aluminate hydrate, aluminosilicate hydrate, calcium sulfoaluminate, aluminum hydroxide, you have the potential to actually form all these depending upon the reactivity of the slag present in your system. So, again concrete properties, the effects are quite similar to what we discussed earlier for general mineral replacements of the cement. Apart from delaying the initial set and strength gain, slag simply does not cause much of change in any of the other concrete properties with respect to mechanical characteristics. Okay. But sometimes you may see that the ultimate strengths with slag are generally improved. That is if you are doing curing. The longer you cure, the better the potential development of the strength. Okay. Now, what is most important is durability, especially in chloride environments, is increased when slag is used as a replacement for cement. That is the main aspect that we want to consider slag for. I will show you some research results later which will capture the performance of the concrete with slag and fly ash as opposed to cement. Now, again here this is one of the results which is actually showing you the size of the porosity with increasing level of hydration. Okay. So, on the right hand side you have this image which is showing a cement with Portland cement replaced by slag, okay, and it is also showing the size of the pores with increasing levels of hydration, and you can see very clearly that the critical radius, that means the largest pore that is still available in the system through which liquids can penetrate your concrete, the critical radius determined from an experiment called mercury intrusion porosimetry. We talked about this earlier also briefly, mercury intrusion porosimetry, or sometimes just called MIP. From this experiment what they have shown is the critical radius, that means this largest pore that is available for liquids like chlorides and water to penetrate the concrete. the critical radius is decreasing significantly with more and more time of hydration obviously, and for systems with fly ash and slag, your pore entry radius is becoming smaller as opposed to that of Portland cement. One important characteristic is for Portland cement there is not much of a change in the pore radius after some time. For Portland cement, after some time there seems to be a stabilization with respect to the pore radius. Slag system again quite similar, right, slightly lower as compared to Portland cement system, but almost it is happening at the same time. With fly ash you see that there is still tremendous benefit of additional curing in the case of fly ash, because again fly ash is much slower to react as opposed to slag. So, more you cure the fly ash system, the higher will be the level of enhancement or reduction of the porosity in your system. Okay. Now, what is shown on the left is actually a modeling of the hydration assemblage that actually ends up forming in a slag system. So, again here what is shown is the volume of the initial ingredients that are present in your system, and what is shown here is as you increase the level of the slag that is there, your hydration products keep changing from the beginning till the end. So, again you have other phases that are forming, essentially your calcium hydroxide phase is getting lower because most of that is getting bound in the other hydration products including calcium silicate hydrate. You may also form some other species like hemicarbonate or monocarboaluminate because of the alumina in the slag. Okay. Now, about that I will talk later when we discuss the limestone calcine clay cement, because that is where this reaction is used to the maximum advantage. Again this is showing some research results which look at the durability of slag cements in terms of chloride conductivity. Again this is not the same test as chloride permeability, but here what you are simply doing is you have chloride solutions at both ends of the concrete, that means there is no diffusion, right. Concrete is saturated with respect to chloride also, that means the chloride from outside are simply not going to get into the inside. What you are simply doing is measuring the charge passing through this or charge carrying ability or the conductivity of the concrete system. So, more permeable it is, the greater will be the conductivity. Okay. The less permeable the material, the less will be the conductivity. So, chloride conductivity is expressed here, and if you are replacing cement with slag, your conductivity is going down tremendously, okay, especially with 50% slag replacements, here 35% slag replacement, here 20% replacement. You can see very clearly that you can maximize the benefits when you are going for 50% replacement with slag. Of course, these are shown for different types of slags. You have the ground granulated blast furnace slag, Corex slag, as well as the ferrous manganese arc furnace slag. So, you can see that the kind of performance you get may be quite different based upon different slags, especially when you are using this ferromanganese arc furnace slag, the performance is not as good as the cement when you are using only 20%. Only when you are using a high amount you can actually bring it to a level which is better than that of plain Portland cement concrete. Okay. So, again you have to be careful about what slag you are using. One aspect you may see these days based on your perusal of different research reports or even websites is that number of people are trying to explore different means of replacing cement with other materials that may be found in different applications. Oftentimes these are done without preliminary characterization of these materials. People simply add this in the concrete and say, okay, I added 10%, the strength changed by 20%. Okay, what is the science behind it? Nobody explains. They just say that I used this, so I got this, and that is the result. But that kind of research we need to be a little bit careful about, because the data may look quite different if you investigate from a different perspective. So, again be very careful when you are trying to look at data which is presented which talks about cement replacement with mineral additives. Make sure that you understand what kind of characterization has been done for the additives to bring out the properties and the behavior of these additives first before you understand how that is affecting concrete properties. Very often that initial characterization is not done satisfactorily, because of which you can't explain the results very easily. Okay. And you know very well from your testing of concrete cubes that you are even allowed a 15% deviation between specimens. You can actually have a 15% deviation. It is not a good thing, but you can have a 15% deviation. So, if you have a research paper which is producing a major result conclusion at the end saying that my strengths are 15% different, it is really nothing to go to town about, right. So, you are not really showing anything new. 15% difference could be because of regular testing practice itself. So, you need to be very careful about how you investigate these claims made by people that they are coming out with new additives. These days especially the amount of research in construction materials has enhanced tremendously. Most people who were doing structural engineering earlier are totally into materials research now. Why? Because there is a lot more scope for doing all kinds of stuff with much lesser cost. If you have to do structural engineering research, imagine how much concrete you would need to actually make a reinforced concrete beam. Concrete cubes, no difficulty at all, you can make it easily, right. So, to cut down costs of research, more and more people, I am not just saying in India, this is happening worldwide, more and more people who were doing structural engineering earlier are starting to get into construction materials research. At the same time, what has happened in construction materials research is that there is another branch of people, the chemists and the materials scientists, who have come in from a completely different background, and they have given a totally different outlook for concrete. Now, those people are doing their research at the cement paste and mortar level, maximum mortar, cement paste mostly, and their results never match with what we actually see in the terms of concrete performance, because they do not understand concrete very well. The structural engineers do not understand the cement chemistry very well. So, ultimately we have a lot of scope for research. So, with that we will stop.